Hello everyone, thank you for coming back. And so this is the third video in the series of learning how to read P&IDs. And my name is Sean Toby, process safety engineer. And yeah, this is promoting safety engineering. So today we're going a bit deeper into the P&IDs, and I just started off with the picture of the entire process of the gas processing facility. And we all know that the end point of this entire process is to deliver gas at a specific temperature and pressure to a power station. So that's why you have all this in here. And so please don't forget to like the videos and subscribe. So I'll go in depth. So I started off with the wellheads. Also, please feel free to leave any comments if you have any suggestions. So I started off with the wellheads, and so these are just the lines. This is the PFD, the process flow diagram, which just is like a holistic form view of everything before you go into the P&IDs, which breaks everything down into more detail. Now, when you see all these P&IDs that they are so crowded, don't be scared. It's really easy to read. Just take your time, know your legends, know your instrumentation. The legends are always up here. This is everything you see inside here is here. It's here. All you have to do is know them and kind of, if you don't need to know exactly what it does immediately, it comes with time, and you can do a lot of googling. Everything, you would find lots of explanation. You can just google types of valves or watch my video on valves. So this flow lines, of course, is the flow lines we have here: 1, 2, 3, 4. That's 17T, 18T, 19T, 20T, but they are just here in a lot more detail. That's 17T, 18T, 19T, 20T. So they are all these lines are doing exactly the same thing. It's just that there are 4 different wells. So we need 4 different lines to all flow into one line, which ends up inside this vessel. That's this line, which is what you would see in the second page here, which is V320 V3020 V3020. So I'll go into this the flow lines here and kind of break them down. I'll break down just one line because that's really all you need to know. The rest are all the same thing, more or less, or they should be. There might be some little errors in there. So these are the lines coming from the well. So you start off, there's stuff and insulating joints, insulating, that says it all. This is a temperature gauge, meaning you want to know the temperature of the gas or the fluid in this stream, in this line. So this is of course a pipe. And when you see a gauge, that means it's localized. That means you have to actually be there to see what's happening. Some of them might actually send signals to the control room, but most times gauges are localized. You have to go there to see them. So then going upwards, these are needle valves. If you go and look at the legend, you would see that these are needle valves, and needle valves are mainly used for kind of throttling, like finely controlling the flow, to control it in a very very meticulous way, just to make sure that you're getting this exact amount of flow. So some of because they are blacked off, that means they are closed. They are not exactly locked closed, but they are closed. They are not open. So you have this here. Then you have the this is also another needle valve. Most times when you lock them closed like this, it's because you want to put future instrumentation like gauges or transmitters on them. So here, this is a pressure gauge. It's different from the temperature gauge. This is just to look at the pressure also. So you come here, you can see what is happening here with the gauge locally. Then you go a little bit forward, you have your PDIA, that's pressure differential alarm. So what happens is, on this line, this is what you call a strainer. It kind of sieves in case there's any impurities, but not everything. It can't catch everything. It's kind of sieves them out, but not 100%. So you have that because you don't want so many impurities going there. So stuff like sand and stuff, you catch them in here. So but that's this strainer. That's why you can see a spool here, a spool here. You can remove it and clean it out in case there's a lot of dirt in it. And that's why you have the PDIA, pressure differential. That means this instrumentation here is measuring the pressure here and measuring the pressure here and trying to know the difference. So if the difference is very high, let's say you are having 5 bar here and then you are having 2 bar here, that means this flow is not, it's blocked. There's something reducing the flow. That means there's a lot of debris, and then you have to open it up and clean it. So that's why you have this most times around the strainers. Then you move a little forward. The next thing you have, this is a valve. It's a motorized valve. That's when you see, normally you see some valves just like this one here. That is just a normal valve. This is motorized because it has this actuator on top. That means it's controlled from the control room or by some trip. And this is the valve, the tag of the valve. Remember, everything is uniquely tagged. All tags are different. All tags are different. So this is 10XZV170 and it's a shutdown valve. So when you see ESD, that means emergency shutdown. That means things are getting seriously out of hand, and then you get an emergency shutdown. When you see OSD, that's like an operational shutdown, meaning for just this unit, things are getting out of hand and you just want to shut down this unit. So this valve does both. It's going to be controlled by some instrumentation that will tell it maybe the pressure here is too much, the temperature here is too much, the level here is too much, and it would either it will close it because it's a shutdown valve. So it fills. That's why you have this arrow pointing downwards on it. That means when it closes, it's the direction is supposed to fill when it's in a closed position. So let's say it loses instrument air, which is used to control these valves. It should close automatically, fail in a closed position. That's what this then okay. So you go forward into this line, and of course we now have a pressure transmitter and an indicator. The transmitter takes this information from this line and it sends it to the control room, where you have an indicator showing whoever is in the control room. So this is different from the gauge. The gauge, you have to be there locally, whereas the transmitter is telling you this is sending the information to some sort of control room where you have your indicator telling you, okay, this is what is happening. And these indicators are also very good because they kind of act as alarms. So if it's low, if the pressure is too low for what you're expecting, let's say you're expecting 5 bar in this line and the pressure is 2 bar or 3 bar, the alarm will go off that this is too low. And if it is too high, you're expecting 5 bar, you're getting 7 bar. That's why you have a H. There's a limit that is set at. If you dig a little further, you can find out those limits, but such information may not be available on the P&ID. But this is just letting you know that there's an alarm in the control room that is seeing this indicator. That's why it's called PI indicator. Transmitter transmits the information. And you also have another pressure transmitter here, but this is working with a PZA. A PZA is a trip, and when you see a trip has high and low, means an alarm goes first before it trips. That means, let's say you hit 7 you are supposed to be operating at 5 bar, but you hit 7 bar. That's high, but the trip may be set at 10 bar, meaning if it hits 10 bar, turn off everything, just shut it off, trip this area so that you don't have more flow going in. And so all those are telling you that there's a lot of instrumentation. That's why you have instrumentation engineers. They do all this to make sure that this process is safe and finely controlled. So you move, you can see there's a drain here, meaning maybe you want to clear out the lines for whatever reason, maintenance. You need a drain to empty everything into. And this is another valve. You go up, so the flow comes all the way like this, comes here. This is also another valve. This is closed, maybe to sample. You have valves for different reasons, and the flow continues this way into this. This is now you have FV, FI, FT. These are all flow transmitter, flow indicator. This is measuring flow, not pressure. So this is telling you, okay, you have this cubic feet going in through, amount of cubic feet going through this place, and the flow indicator and flow transmitter control this flow valve. That's the FV, flow valve. So when, let's say, there's too much for what it's set at, let's say it's to be going at 100 meter cube per second, and then it's in 150 meter cube per second, it's immediately tells this that close this valve. It's a control valve. That's why you see 10 FCV 170. It's a flow control valve. So it will tell it, okay, close it a bit because the flow we are seeing here is too much. Oh, if the flow is too low, open it a bit. So it keeps on going up and down, trying to get the required amount of flow for the operating parameters for the system. And going from there, you come here. This is another valve. This is used for chemical injection, not in use. So what's chemical injection? It means stuff like corrosion inhibitor. That means maybe the line, you don't want it to get corroded at some time in the future. You are thinking that maybe there may be too much water in the fluids and you don't want to have corrosion. So you have some corrosion inhibitor or hydrate inhibitor. There are different kinds of chemical injection. It's all term chemical injection, but it's to inject some stuff to help with the flow, with the process. It's flows into it, mixes with it, and keeps on going downwards. It always comes with pumps and stuff to just join into the flow. Then you go forward again. Then you have more pressure indicators, pressure transmitters, pressure gauges, all. And then, okay, we haven't talked about it. This is a non-control valve. That's why you can see this direction arrow on it, meaning non-return valve, sorry, meaning you don't, or you can also call it a check valve, meaning it's a valve that only allows flow in one direction. Flow cannot go backwards. Once it goes, there's like a flap that stops the flow from going backwards, so it only allows flow in one direction so that you don't kill your well. And then you have your flow indicator, flow transmitter, and then you go all the way into okay, so then here is also another emergency shutdown valve and operational shutdown valve to control the process. Again, you have them a lot because that's what helps you control your flow, and you go all the way to train 1. So that is this, and the same thing runs through all these other lines. Sorry about that. All the same, it's the same, but the instrumentation, the nomenclature would be different. This 171, 181, 191, 201, like that, because you want to uniquely tag everything. So everything, all these lines, they're all the same. They all flow all the way into this. So you have your flow from gas from inlet manifold coming in here and hitting, and so hitting this is called the HP knockout vessel. And if you go back to your, that is this, your PFD, that is this. So you have all those lines 1 2 3 4 coming into this, and then so before it goes in, you have your pressure gauge, checking the gauge before you go in here. Then you also have your transmitters all around the vessel, just to protect that vessel, to make sure we are at the normal operating temperature, operating pressure, operating temperature, operating pressure. And so you have your, all these are all localized on this vessel. You have your level gauge, you have your level transmitter, you have your level trip. Anytime you see L, that's level, and that's just dealing with the liquid. When you see P, that's pressure. That's mainly like the gas. It's the gas that causes pressure. So of course, you have those trips too. In case the level in the vessel gets too high, you have your high trip here. And if the vessel level in the vessel gets too low, so you don't have a liquid blow by or a gas blow by, you don't want that, because if the liquid gets too low, gas can go to where it's not supposed to go, to the liquid leg. So you have that. You have your level gauges here, level transmitter here, all taking the readings from here. So this is transmitting that information all the way to to the control room, and then you have your alarms too. When the level is too high, the alarm goes first. If it's too low, the alarm goes first. If it gets really high, after the alarm, then it trips off. And if it goes too low also, after the alarm, it trips off. You can see all of them around the vessel, all protecting the vessel. So you have your level, your temperature, and then so remember, the vessel is supposed to push out flow in two directions. For this vessel, the top is the gas leg, the bottom is the liquid leg. So you have gas flowing out from the top here, and at the top of most vessels you have a PSV, that is pressure safety valve, meaning if the pressure gets too much. So there are different levels of protection. You have your pressure, your pressure gauge here. Okay, that means this is not going to see so much pressure. You have your pressure transmitters here, so you can see this is a high and low. So if the pressure in this line, which is a result of the pressure in this vessel being too high, you have your high alarm and your low alarm. It sends the signal straight. The pressure is too much, it alarms. If nothing is done about the alarm, it goes to trip off. Can you see OST, operational shutdown? It trips it off, high or low. It will trip off this whole vessel, most likely closing the inlet. And that's why you have your cause and effects too. You can see what the uses of all these strips are for, what it closes, what it opens. And then, so let's say an alarm goes off, nothing is done about it. It doesn't trip, then, or it trips, then you have this is your last line of defense, your pressure safety valve. This would now pop open and send all the excess gas to the flare. Can you see, to the flare header? That means these things are really getting out of hand, and so this just pops open to relieve the whole situation, because gas at high pressure is one of the major hazards in a gas plant. So you have all this there to protect, and then you have your pressure gauge. You have you have all these gauges, because at every point in time you want to know where things are going wrong. You don't want to, you can't just have one like in the page before and use it for everything here, because you don't know if the problem is from here, you don't know if the problem is from here. So that's why you have so many of this instrumentation, and then from there the flow goes into the exchanger. So this is the choke exchanger, and what it does, it's a heat exchanger. Flow is coming in from this way, going this way, and another flow is coming in from this way and coming this way. So you look at all those. Okay, so the flow here comes here. That means probably you want to heat up the gas, comes all the way. You have your temperature indicators, your temperature transmitters, all letting you know, okay, since this is exchanging temperature, it's either heat or cooling, you want to be able to actually finely tune it, finally know what's going on. That's why you have your temperature trip, TZA, high, low, and the same thing. You have your flow here at the bottom also telling you. So this flow goes all the way into page 22. And right now we are on page 21. Oh, sorry, 20. So page 22 is 2 pages below. So you don't always expect the P&ID to go exactly the way it's arranged, because you will have this is going to page 22, but you have another leg going to page 21, which is the next page, which is the liquid leg. Also, you have your liquid coming out this way, all the way this way, and here. So, but let's look at the gas leg. The gas has gone to page 22 now. So if you look at this 4-inch 2582 12102 12102, remember that. So we go to page 22. So we are looking for 12102. Yeah, this is it. So this is that line coming from, can you see, page 20, 4-inch PG 25822. So this is the gas. So it comes in here. So it's GHP gas from choke exchangers. You've seen where the line comes. You are looking at, okay, so that is where that gas leg goes to. Then you want to look at where does the liquid leg go to also. The liquid leg comes out from here, goes through this flow transmitter, and goes all the way into this line, which goes to the classifier exchanger 21, and also this second line to goes to the classifier exchanger. There's a reason why there are two here. You can see this non-return valve, you can see the flow transmitter, flow meter here reading everything that's happening in here. So you have this line. I need to get the line number, 3-inch, this 12015 and this 12085, and this is going to page 21. So you have 12015, 12085. So you see 12015 from HP Knockout 12015. That's the same line coming here. And where is 12085? That's the same line coming here. So we'll go more into a lot more detail, but thank you very much. I will continue from this page in the next video. I don't want to make them too long so you don't get bored. But so right now we are on we've looked at some page 21 and page 22. So I will start from 21, 22 because I'm through with 20, and break them a little bit further down and see how far we can go. So thank you very much. Like, subscribe to the channel. Thank you. This is Promoting Safety Engineering, and my name is Sheon Toby. Thank you very much once again. Do have a lovely one.